And welcome to an introduction to the distribution of sample means. So the idea here is that we use samples instead of the population to study what might happen to the population, right? So if we want to study the population mean, if we want to study the population mean, we instead pick a sample. Find the sample mean. And use it to make inferences about the population or about the population mean. But the problem here is that the sample means might not agree with the population mean. And so we need to know, kind of just like we did with the sample proportions, we need to know what might happen with the sample means. But the sample mean will likely be different from the population mean. Let me give myself a little more space. So it will likely be different from the population mean. So we need to study what might happen with our sample means. So we're going to look at a very small scale example to start off with. So let's consider a family with 5 children that are aged 2, 4, 7, 9, and 13. First thing you want to do is just figure out what is the mean or average age of the children. So the population mean, we have a tiny population, but this is the population. We'll do 2 plus 4 plus 7 plus 9 plus 13. And then divide by, we have 5 children listed. So this becomes 35 divided by 5, otherwise known as 7. So this population has a mean age of 7. And then I've gone ahead and found all of the samples of 3 of their children. So we're going to then take the mean of each of these samples of 3. There are no other possible samples of 3 of their children. There were only 10 possibilities we could pick. So this first one, the mean, we have 2 plus 4 plus 7 divided by 3. That's 13 divided by 3, otherwise known as about 4.33. For the next one, x bar, we would do 2 plus 4 plus 9 divided by 3, which is 15 divided by 3, otherwise known as 5. Then we have 2 plus 4 plus 13 divided by 3. That's 19 divided by 3, otherwise known as 6.33. Next, our mean, we're looking at 2 plus 7 plus 9 divided by 3. And that would be 18 divided by 3, or 6. The next one we have 2 plus 7 plus 13 divided by 3. And that becomes 7.33. Next one, we are looking at 4 plus 7 plus 9 over 3. And that becomes 20 over 3, or 6.67. Then we have 4 plus 7 plus 13 over 3. And that is 24 over 3, or 8. Next up, we have 4 plus 9 plus 13 over 3. And that is 26 divided by 3, or 8.67. Then we have 7 plus 9 plus 13 over 3. And that is 29 over 3, or 9.67. And then last up, 2 plus 9 plus 13 over 3. We are looking at 24 over 3, or 8. So these are all of the means from our 10 possible samples of size 3. So from here, we are going to make a dot plot. So the smallest we went was 4.33. The largest we went was 9.67. So let's do 4, 5, 6, 7, 8, 9, 10. So we had 4.33, 5, 6.33, 6, 7.33, 6.67, 8, 8.67, 9.67, and another 8. All right, so again, the data values range from 2 to 13. Our means are now from around 4 to 10, with most of the means sort of between 6 and 8. So the sample means certainly do not match the population mean. The population mean was 7. Our means sort of are around there, but not precisely 7. But this is the distribution of sample means for all samples of size 3 from this small population. Now, in reality, there's no reason to pick a sample when we only have 5 individuals in our population. Usually we are working with much larger populations. So next up, we're going to consider a simulation. And this simulation is looking at, if we use, say, cash at a store, we often get change back. I'm going to ignore the dollar component of the change and just look at what we would get in coins, so the cents component of the change. So we're going to look at the change in coins from a transaction at a store. And we have a list of the change from 1,000 transactions. And those amounts of change have a mean of 0.498 and a standard deviation of 0.289. And then we are going to focus on samples of 30 transactions and then record the sample means from those. So we're going to find this simulation at rossmanchance.com/applets/onesample.html. And if we go here, I am going to use change is what we were talking about. So here's my list of transactions. So transaction 1, the change was 97 cents. Transaction 2, the change was 99 cents. And we have a lengthy list of transactions with a variety of sense. So if we just study this population, so the mean is 0.498, the standard deviation is 0.289, and there were 1,000 transactions. So here's a histogram of the distribution. It's relatively uniform. I mean, this is definitely not a normal distribution. There were plenty of transactions that had basically zero change and plenty of transactions that were very close to $1 in change. So what we're going to do now is we're going to look at samples. So let's just take one sample, and then we're going to do samples of size 30. So let's take one sample of size 30, and here's my sample. So you can see which transactions were chosen. And now there's only 30 transactions in this, as opposed to the 1,000 transactions we had. I accidentally hit reset there, so let's just redo this. Okay. So here's my sample. So these are the transactions that were drawn. And this particular sample had a mean of 0.483 and a standard deviation of 0.285. And then over here, this is just the mean of that sample was 0.483. So now let's go ahead and do this a few more times. So here's another sample. The numbers have changed. This sample has a mean of 0.563. And now if I look over at the means, we have our first sample mean at 0.483 and our second sample mean at 0.563. Let's go ahead and do one more on its own. So doing one more, here's our next sample. This one had a mean of 0.538. So now over here, I have bars at 0.483 for our first sample, 0.563 for the second sample, and then 0.538 for our most recent sample. So now let's go ahead and do a whole bunch of these samples at once. So let's go ahead and jump up to another 597 samples to get us up to 500 samples in all. This was the most recent sample of 30. And then here's what happened with all of the different sample means. So that blue line at the very top is this most recent sample, which had a mean of 0.493. All of those means that we previously found are counted in this. This is now portraying all of the different sample means that we got from 500 different samples. As you can see, this set of 500 samples, the mean of the sample averages was 0.494. Standard deviation was 0.052. And now this actually does look more or less like a normal distribution. So the data itself fit a uniform distribution. But once we look at samples of size 30, take a whole bunch of different samples of size 30 and study their sample means, it now becomes a normal distribution. So this was playing around with our, or sort of a basic distribution of sample means from our data set. So in the next video, we are going to play around a lot more with this simulation, but this was just a rough introduction.